Our topic for today is topic 21, electronic from CAIE syllabus. Follow the syllabus directly. Right? What are the things we are going to cover? Right? From topic 19.4, sensing devices. From 21.1, we are going to look at ideal operation amplifier. And 21.2, operation amplifier circuits. 21.3, output devices. So basically, under sensing devices, we look at electronic sensor, LDR, thermistor, piezoelectric transducer, metal wire strain gauge. Under ideal operation amplifier, we look at operation amplifier as comparator. And under amplifier circuits, we look at effect of negative feedback. The original operation amplifier is of not much use to us unless we have a negative feedback, which is more useful. Then we have the inverting and non-inverting. Then we need to know what is gain of amplifier. And finally, we need to know the output devices. These are input devices. It senses what is happening in the environment. This is the output device telling us either visually what happened, like LED, relay, digital, and analog meter. It tells us the voltage has changed. Okay, or in pictorial form, that is the circuit setup for fire alarm. We look at input devices, or we call sensing devices. Piezoelectric crystal, that's what is happening. There's a piezoelectric crystal. There's a voltmeter. As we change the pressure across it, there's a voltage. We can see the voltage changes also. Then strain gauge. There's a LDR. Microphone. There's a symbol of microphone. And processing unit. We are interested in operation amplifier. There's the equivalent circuit. And we look at it as a comparator. As a comparator circuit. And this part is the input voltage, this part. And that part is the comparator. And this part is the output voltage. But as we say, the gain is too high. And there are also problems there. That's why we have negative feedback. There's a negative feedback resistor. This one either inverting or non-inverting amplifier. We look at them. Then the output of this amplifier or whether of this comparator, we must have something to tell us what is happening. Right? So we have output devices. We have relay. Relay. LED show us visually by the color of the light what has changed, or a loudspeaker, or it can be a fire alarm warning us something is wrong. There are rare resources that CAIE has given, and the examiner provides booklet to make the syllabus content clearer, but you must always think that it's not authoritative guide, just a guide, just to help you understand the formula, what's requirement of the syllabus. Right? There are textbook, there are various textbook that you can use if you want to read further into this area. There's a past year paper, 125, page 140 to practice. Right? Traditionally, you may see this one if you have a grandfather who keep this one. That is your used to be a valve. Right? Today we won't see this anymore. Probably in museum or second-hand shop because it's too expensive to maintain. Okay, was used in this type of vacuum tube is used during the until 1950. Right? Physics got many branches. You got nuclear physics, you got study of semiconductor device related to technology, area under thermodynamics. As you go higher and higher, you become more specialized. And you got others. Electronic is probably one of the branch. And if you want to go into greater detail, electronic engineering, I tell you design and construction electronic circuit to solve practical problem. Here, physics, we study the theoretical part. Engineering, we apply what we study to build things that solve our practical problem. Right? So today you see more of this type of thing. Electronics. Right? Which are made of semiconductor. Maybe we can see a video. Okay, let's look at the video of piezoelectricity. There's one of the input sensing device that we are interested in.
This is a piezoelectric element that we obtain from a buzzer like this. Here we have the piezoelectric element connected to a voltage meter. When the element is pressed, a voltage is produced. We can see that voltages of up to 20 volts are obtained. For a useful circuit, we need more components. A diode has been added to the piezo element in order to rectify the output, and a capacitor to store the energy that we produce. As we press the piezoelectric, the capacitor starts to charge and the voltage increases. Now let's make a slightly more complicated circuit, adding a LED and a switch. Here's our circuit. We have the piezoelectric element connected to the capacitor through a diode. The diode rectifies the output from the piezo. We have the LED, the resistor, and the switch. Let's now turn off the light. And when we press the switch, the energy stored in the capacitor is used by the LED. Now we need to charge the capacitor again. So we press the piezo, and as we pump, the energy in the capacitor starts to rise, the capacitor charges, and the LED lights when we press the switch. We can charge again and repeat the process in order to use the energy that we are producing with our element.
Okay.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter.
All right, this is a really quick video about taking a piezoelectric transducer and making power. So here's the transducer. I have the outputs attached.
Okay, let's go back to our physics. Okay, let us start with our sensing devices. Okay, that's the syllabus requirement. Right? Show an understanding of the change in resistance with intensity of light-dependent resistor. Sketch the temperature characteristic of a negative temperature coefficient transistor. Show an understanding of the action of piezoelectric transducer and its application to a simple microphone. Okay, we have already seen the video on piezoelectric transducer. Describe the structure of a metal wire strain gauge. Relate extension of the strain gauge to change the resistance of the gauge. Okay, so that is taken from 2012 November paper 43 from CIE exam. It's an electronic sensor to monitor whether the temperature in a refrigerator is above or below a particular value. That's the input. So we will identify what is F and then what is E later on. Right? This part is called the sensing devices, especially this one. This is your thermistor. This is your variable resistor. Allow you to adjust the temperature that you want. So usually we want to draw that complicated circuit. We just want to represent it as a sensing device. And the other one is a processing unit. So sometimes we just want to draw that rectangle, call it processing unit. And same with the last part, the output, right? It's a LED. Yeah, it can be different color. It should indicate the temperature of the surrounding of the refrigerator. So that's the output device. So this is called a block diagram. It's easier. Right? We don't need to draw what is inside and it's faster. But it tells us what is happening. Simplify for us. Right? Can we draw that block diagram of electronic sensor? We need a sensing device. A sensing device gathers the information by change in physical property. We look at it later on, just like just now there. Right? The thermistor sense a change in temperature. Then the resistance changes. And we feed the change in voltage to the processing unit. Processing unit give an output, right? Communicate this output to the output device. So output device indicate the change. It can be indicator lamp, it can be LED, it can be a meter, and we can read the change. So a thermistor sense a change in temperature and the LED indicate the change in temperature. Rather than every time we have to use a thermometer to measure the temperature, we can use your thermistor and the LED indicate the change in temperature in the refrigerator. Right? There are other examples. You can use block diagram. Right? Your computer, your keyboard is your input device. You tell what you want to do on your keyboard. Microprocessor or the CPU in the computer. Right? It processes what you want and then it display on the VDU, visual display unit, what the output, what you have done. or you can have a needle and cartridge. Right? We amplify the sound for you, and our speaker give you the sound waves. Right? This is a mechanical motion, amplify for you the voltage, and then this one give you the sound output. So there is also a record player, which is also now you probably won't see in many houses because it's not popular now. Right? So this is temperature sensor. Temperature of surrounding increases. What happened? The resistance changes. Resistance decreases for this one. So it means that there is less resistance here. Potential across here will increase. And the comparator will receive the increase in voltage and send it to the output there. And then we can use different color to indicate the temperature of the environment. There is a sensing, there is a whole circuit or temperature monitor. So always remember the sensing device is the first stage of any electronic sensor and is the means by which whatever is to be detected or monitored is converted into electrical property. In this case, the change in the environment temperature changes the resistance, that's the electrical property. And this electrical property causes the voltage to change across the resistance. So the physical property of the sensing device changes with a change in whatever you are monitoring. If the change in temperature and change in resistance. If you want to monitor the light intensity, then you use your LDR, light dependent resistor. So these are what we will be interested: light dependent resistor in the syllabus, thermistor, piezoelectric transducer, strain gauge. You'll be looking at them. That's a symbol for piezoelectric. Piezoelectric crystal. There's a two electrode connected to the crystal. So you should be able to identify in your exam. There's your thermistor. This is your strain gauge. This is your LDR. This is the symbol. And then this is a symbol for microphone. Light dependent resistor is made of cadmium sulfide. Cadmium sulfide is a semiconductor material whose resistance varies with the light falling on it. Made by sandwiching, like a sandwich. Right? The film, sandwiching a film of cadmium sulfate between two metal electrode. Between them, you sandwich your cadmium sulfate. So as a name implies, light, it depends on the intensity of light. LDR is sensitive to changes in light intensity. Light intensity change the resistance, but the resistance and intensity is not linear. The change in resistance is not linear to change in intensity. As light is absorbed, what's happening? By the material, electrons and positive holes are released and become available for conduction. That's why the resistance decreases. In moonlight, it means dark. The resistance is 1 mega ohm. It means high resistance in darkness. In sunlight, bright light is 100 ohm. We consider as low resistance. LDR are used in electronic circuit to operate light sensitive switches. Remember, used as switches. Just now we look at temperature sensor. Is a switch also, telling us by the indication of light the change in temperature environment. For example, they can be used to switch on light automatically when daylight gets too dim. Rather than we do the thing, the electronic device can do for us. If light get too dim, you can turn on the light for us in the room. That's the symbol for your light dependent resistor. Think of it as there's your resistor, actually seal up, and there's a blue arrow representing the light. Then we come to thermistor. You can see that different shape. And on the ruler will just give you the size of the thermistor. So it add to sense temperature change. Right? As thermostat to keep the temperature constant. And it can also be connected to an alarm. Right? Tell us that, yeah, there's a fire in the room, warning us. Or also, freezer, something is wrong in the freezer. Go and check, malfunction. Right? It can vary, manufacture in various shapes and sizes using oxide of different metal. So there is significant change in resistance with temperature. Right? Resistance change with temperature. It's made of semiconductor material. A rise in temperature releases more electron and positive holes, improving the intrinsic conduction of the material and so lower its resistance. Right? As temperature increases, there are more electron and positive hole available for conduction, so the resistance decreases. That's the symbol for thermistor. And there's the graph. Resistance against temperature graph. Right? It's not a straight line, it's not linear. Right? It's a curve. Right? We call it negative temperature coefficient, or NTC. N for negative, T for temperature, C for coefficient. This is the one that we are interested in. We're not interested in PTC, where there's positive temperature coefficient, the resistance increase with temperature. We're not interested in that. We're interested in this one, where the resistance decreases with increasing temperature. Right? Resistance becomes less as the temperature of the thermistor rises. Right? Sensitivity, you can get it from the gradient of this tangent to the curve. Comparatively large change in resistance with temperature at low temperature. This is low temperature here, that's high temperature. And we can see that the slope is greater here, very sensitive. And here, towards the end there, high temperature, about 51 or 70, be 51 to 70 degrees, the slope is very small. So the sensitivity is also very small. And we know the graph is not linear, it's a curve. Remember, sensitivity is the rate of change in resistance with temperature. And it's the gradient of tangent to the curve. Sensitivity is large at low temperature. At this part there, gradient is large. And at at high temperature, sensitivity is low. Gradient is smaller. Right? There are practical uses of thermistor, thermometer. Being initially cold, they have a high resistance. What's the advantage? The advantage is that in certain circuit, we do not want the high current to flow when we switch it on. Example, a lamp or motor. We don't want the current to flow very, very fast or very high current. It may damage the lamp electric motor. So if it's cold, it has high resistance. If it has high resistance, the current will be very small. Only as it starts to warm up, then the resistance decreases, then more current flow. Right? So that's a practical uses. Protect the lamp or electric motor the moment we switch on. Right? Sometimes can operate thermostat as thermostat. Right? Sense the temperature of surrounding. If it's too cold, then you can switch it off to let it warm up, or to activate a fire alarm. Right? So you can think of it as used to switch electrical circuit when the temperature changes. So it's a temperature sensor or heat sensor. Then you got piezoelectric crystal, that's how it looks like. Right? Example would be quartz. They have a complex ionic structure. You want to look at some of these, right? Get more information in YouTube. There are some of the uses. Right? As a piezoelectric element, as your gas, right? Produce the spark there, light the gas. That's how it looks like. Piezoelectric device. Or we will see some of the LED light as you walk. When you see light on the LED device in your shoe, then there's the uses there. Or we can use it, like in some country, they use it as you walk. You press on the crystal, it can generate electricity, light up the road for you to walk, to see. So it saves you, public lamp. How does it work? Right? There's a crystal there. Basic idea is there's no PD across it, where there's no pressure. But when you stretch it or you compress it, there's a potential difference across the crystal. Like you can see from this voltmeter. This is a piezoelectric crystal. As it compress and stretch, there's a potential difference. Whether it's positive like this case, it depends whether you stretch it under tension or you compress it. Right? So the polarity of the output depends whether it's tension or compression. Right? We can think of it as this is your structure. Right? Silicon at the center there, silicon are positively charged, ion and oxygen. At the end there, this is 2-dimension drawing. It's a 3-dimension drawing. There's an oxygen at the end there. Okay. Same oxygen there, oxygen negative ion, positive ion. So if you unstress, basically the centers of this negative charge and this positive charge go inside. So there is neutrality, no potential difference across the crystal. Right? Unstretched, CG or positive and negative charge go inside. So neutral, no potential across the crystal. But when you stretch it, right? When you stretch it, what is going to happen? You are trying to pull this positive up. So now the positive and the negative centers doesn't coincide anymore. Right? Positive and negative charge do not coincide anymore, the center of gravity. So the top part is positive, bottom part is negative. Or when you compress it, the same thing, you're pushing the positive down. Right? The top is still negative. So the positive and the negative charge do not coincide. So now the positive is at the bottom. The up there is become negative. Right? That's explain why we have change in potential difference across the crystal. There's no stress. When not under compression or tension, the center of gravity of the positive and negative charge go inside. Okay? Just to show you, unstressed, no PD across the crystal. Right? When it's compressed, right? Or when you apply the pressure to the crystal is distorted. Centers of positive and negative ions no longer go inside. The voltage will be generated across the crystal when the pressure is applied to the crystal. And this is known in a piezoelectric effect. Whether it's compressed or stretched, the potential across a crystal will be different. Magnitude, right? You can measure using a voltmeter. How does the magnitude depend on? Magnitude of the voltage you generate depends on magnitude of pressure. Greater pressure, greater voltage. Polarity depend on whether it's compressed, you compress the crystal, or you stretch the crystal. Right? Whether increase pressure or decrease the pressure, same thing. Right? Remember, sound is a mechanical wave or pressure wave. Compression is where the pressure is largest. Rarefaction is where the pressure is the least. So as you speak, the sound wave travel as longitudinal waves, as pressure waves. So when the sound wave fall on the piezoelectric crystal, right, remember sound wave is changing, sinusoidal. So a varying voltage across the crystal will be produced. And if it's too small, we can amplify it. The crystal and its amplifier act as a microphone. Example, that's where we use as a microphone. There's a piezoelectric crystal, there's a diaphragm. So basically, that's a symbol for microphone. So as the sound wave comes, it will cause the diaphragm to vibrate, and the vibration will be transmitted to the piezoelectric crystal. So the vibration will cause it to stretch and compress, and the voltage changes, alternating voltage changes, will be converted by this wire back to your processing unit. So this is the input sensor. So basically, microphones are transducer which detect sound wave and it produces a voltage or current proportional to the sound signal. Right? Instead of sound, it converts it to electrical signal. Okay, so this is basically your piezoelectric. It's very thin strip of piezoelectric material attached to a diaphragm. Two sides of the crystal acquire positive charges when the crystal is deflected. Okay, so one side will be positive, one side will be negative, depend on whether it's compressed or stretched. There's your strain gauge. That's where you solder it. And it's made by sealing a length of fine wire. There's your length of fine wire. Okay. In the plus, there's your length of fine wire. And your backing material, or the one over it, the backing material is a thin plastic. Strain gauge are usually glued very securely. Doesn't want it to move. To the material that's under test. You want to study about the material under stress? Just do a strain gauge on it. How does it work? When the plastic is stretched, you experience a strain, increase in length. The wire will also be stretched. And let's look at the physics involved. Strain gauge, stretching. Right? That's the original length, not stretched, unstressed. Piece of wire, that's a cross-sectional area A. So when we stretch it, it causes the wire length to increase, the cross-sectional area, the cross-sectional area, the length increase, cross-sectional area to decrease slightly. And you can remember our resistivity, our resistance equals to resistivity rho L divided by A. It means our resistance depends on length and cross-sectional area. So when you stretch it, if you're pulling it with a force, the length increase, the cross-sectional area decrease, so So both changes will affect the resistance, will cause the resistance to increase. Okay, let's look at the physics involved. Change of resistance with extension for a wire. Right? The resistance is given by this formula. R equals to rho L over A. L is the length of the wire. A is the cross-sectional area. Rho is the resistivity of the material. Right? We want to make the math simpler, so we assume that when the wire extends by a small amount, delta L, the cross-sectional area is negligible. That means no change in cross-sectional area. The new resistance will be given by that. It means if we increase the length by a small amount, the resistance will also increase by a small amount, delta R. Okay, let's do some subtraction. Delta R is a change in resistance, a small change in resistance. Just rewrite the two formulas. There's a change in length, there's a small change in resistance. So we can subtract. Right? Remember, we assume our A is constant. So subtracting 2 from 1, okay, R and R subtract goes off. We still got delta R here. We got rho L over A, subtract rho L over A. So that one goes off, but we still got rho delta L over A. Okay, that's what we get. Remember, our rho and our A are constant, doesn't change. So it means that our change in resistance depends on change in length. Right? Or the strain is proportional to the resistance. Change, we just divide. Strain means we just divide this delta L divided by L itself. Right? There's the uses. Attach it to whatever you want to study about the bending of this structure. Or I want to study about that rod as under stress and strain. Mechanical casting. So we can summarize about transducer, any device that converts energy from one form to another. Microphone, we convert the sound input into alternating current or voltage. Loudspeaker, it convert the alternating current to sound wave. LDR, we use in light meters. Variation in light intensity, it convert to current variation. Pickup cartridge or record player, right? Mechanical vibration. As the needle move up and down, record player, it convert it to alternating voltage or current. Okay, so these are various transducers. So we can summarize what we have studied. Transducer, any device that converts energy from one form to another. Right, there's an example. The LDR. Right, so the input sensor gathers information about the physical change of the environment. Right, you have the light-dependent resistor. The intensity causes a change in resistance of the LDR. Darkness, high resistance. Bright light, low resistance. Then there's a symbol for your thermistor. Same thing. High temperature, low resistance. Low temperature, high resistance. Okay. Used as thermostat. Okay, let's look at some of the questions. You likely to encounter exam 208 June. Right? They ask you a block diagram for electronic sensor is shown in figure 9.1. Complete 9.1 by labeling the remaining boxes. Right? Sensing device, processing unit, output device. Question 2. Right? You need to know what each of the symbol represent. Identify the following. A, that is A. Right? Be able to recognize by now. There's a thermistor. Then B is your variable resistor. C and D together is a potential divider. Right? A and B is also a potential divider. E is your light emitting diode, or two of them, different color. And then F is your operation amplifier. The amplifier we are interested in this topic. What does it do? Thermistor, you should know, is a heat sensor, right? Or it senses the change in temperature environment. What happens at high temperature? Low resistance. And when it's cold, yes, high resistance. What physical changes in thermistor? Resistor is the one that changes. Right? Light dependent resistor, what does it do? Light sensor. It changes with intensity of light. What happens in bright light? And roughly you should know the resistance involved. Right? Low resistance at bright light. Because if the light is a semiconductor material, it produces electron and hole pair. So it improves the conduction. So low resistance for 100 ohm. Darkness, high resistance. Resistance is about 1 mega ohm. What physical changes in LDR? Resistance. Right? Changes in resistance. What is piezoelectric effect? A voltage will be generated across a crystal when pressure is applied to the crystal. Polarity of the voltage on the crystal depends on whether it is compressed or stretched. That's all. Potential divider, we will encounter this again in electronic. Right? What is the syllabus requirement? Understand that electronic sensor consists of a sensing device and a circuit that provides the output that can be registered as a voltage. Explain the use of thermistor, light dependent resistor, and strain gauge in potential divider to provide potential difference that's dependent on temperature and illumination and strain respectively. Okay, so we are basically reviewing the potential divider. That's where the users is. Right? Monitoring the temperature of a refrigerator. Is that a refrigerator? So that is your thermistor, right? This one, potential divider. So the change here will affect the potential across here. And it is fed back to the operation amplifier. And then these two provide a constant potential difference across this positive input. Okay, so let's just review what we have studied in your AS. Converting the output from a sensing device to a voltage. So S is your thermistor, R is your fixed resistance, that's your EMF of negligible internal resistance, V is a potential difference across S, V1 is a potential difference across R. A change in resistance of these sensing devices S, you change the resistance, there's a change in voltage across here. So the output voltage at V, output voltage depend on S divided by S plus R times E. EMF is the EMF of the cell is a constant, no internal resistance. That's your resistance. R is the resistance of the fixed resistor. S is the resistance of the sensing device. Right? Magnitude of the output voltage, that is your V. We take it across S, that's the output voltage. At a particular resistance S, right? You can see from the formula, particular S depends on S and R. A change in S will give rise to a change in V. So we can see that if that changes, it affects this one, but it will affect this one also. V. E is constant. So if our S decreases, then our output voltage, right? This one decreases, this one also decreases. Whereas V1 will increase. Right? Think of this as constant. If this one take less voltage, this one will take more voltage, a sharing. Right? Think of potential divider as sharing the voltage of the EMF. Changing any of the resistance changes the current. Don't focus on current. It doesn't affect them at all. It affects both equally. The new current affects both resistance equally. EMF is constant. The greater the resistance has, right? The greater that resistance, the greater will be this PD. Because your potential difference is proportional to resistance. So if that resistance is larger, then it has a greater V1. That's what it means. Greater share of this EMF. This EMF is fixed. Right? So if this is larger, it has a greater share, V. So you must connect across a correct resistor. However, connecting the output across the fixed resistor means that V1 increases when S1 decreases. Right? Where there's an environment temperature decreases, that resistance will decrease. That potential difference will increase. Right? So it's important that we connect our output across R rather than S, because we want the increase in temperature, increase in the voltage, reflected there. So hotter, decrease in voltage here, decrease in resistance here, but there's an increase in R. R the same. So they increase in V1. Okay, or if you want to monitor the changes in temperature with time of the environment here, you should not take it across here, you should take across R, where you will show how the voltage will change with time. That means you want the variation of temperature time as a voltage temperature time graph. Okay, thank you. We have completed that. So we'll end. Before we end, let me just give you some more information. Okay, as I say, you can go to Facebook. Right? That's where all my notes will be placed there. The PowerPoint, the video. You download it freely. Or you want to pass your paper from 2001 to 2010, topic by topic. You have to practice it. You have to practice it to show your understanding. You can download it from Physics Past Year Paper A2. Or you don't have access to Facebook, you can always go to YouTube to download all the video of my teaching from. Google my name and then go to YouTube. Go to YouTube first and Google my name, then you'll find all the video there. Okay, A-level revision. You can find it there. So thank you. So we'll end now.